For decades, there's been this invisible war raging inside the human body. The enemy? One of modern medicine's most formidable challenges, the human immunodeficiency virus, or HIV. Today, we're going to pull this virus apart, piece by piece, to really understand how it operates and why it's been such a tough opponent to beat.
So here's our game plan. We'll start with a proper introduction to the virus itself. Then we'll get into the nitty-gritty of its anatomy, almost like we're studying its weapons. After that, we'll watch its strategy for a total cellular takeover, map out the stages of infection, and finally, look at how our modern defenses can actually spot this intruder.
All right, first things first, let's get formally introduced. We're about to get to the very heart of what makes the human immunodeficiency virus so unique. You see, HIV isn't just any old virus. It's a special type called a retrovirus, and this gives it a seriously powerful and kind of sneaky ability. Now, most life, including you and me, follows a central rule. DNA makes RNA. But HIV, it works backwards. It carries its genetic code as RNA, and then it uses this special enzyme, it's called reverse transcriptase, to literally rewrite that code into DNA. And the craziest part? It then permanently stitches that new DNA right into our own genome, effectively turning our cells into little virus-making factories. It's a truly devious survival strategy. It's also really important to know that we're not just talking about one virus here. There are two main types. HIV-1 is the one you hear about most. It's the global powerhouse, it's more infectious, and it causes the disease to progress much faster. Then there's HIV-2, which is less common, not as aggressive, and is found mostly in West Africa. So for the rest of this breakdown, we're really going to be focusing on the big one, HIV-1. Okay, next up, let's do a little threat assessment. We're going to break down the individual virus particle, that's called a virion, to really understand its structure and, well, its weaponry. Let's build this thing from the inside out. Right at the very center, at its core, you've got two identical strands of RNA. Think of it as having a backup copy of the genetic blueprint, along with that all-important reverse transcriptase enzyme. This core is protected by a cone-shaped shell, or capsid, made of a protein called P24. Around that, you have the P17 matrix, which is a protein layer that's kind of like chainmail armor. And finally, you have the outer envelope. This is the part that's studded with the proteins it uses to invade our cells. Now, these components aren't just thrown together randomly. Oh no, they're meticulously built from instructions in three main gene groups. You've got the GAG genes, which build the physical structure, like that P24 capsid. Then the POL gene creates the functional enzymes, including reverse transcriptase. And finally, the ENV gene is responsible for those envelope proteins, the very keys the virus uses to unlock and get into our cells. And now, for the main event, the invasion. How does this perfectly engineered virus actually get past our body's defenses and take over our cells? This is where the story gets really clever. See, HIV is a highly specialized hunter. It doesn't just attack any cell it comes across. It specifically targets the generals of our immune system, our white blood cells. Its primary targets are helper T cells and macrophages, and they both have something in common, a specific marker on their surface called CD4. So how does HIV get inside these cells? Well, it uses a brilliant two-part entry system, a lot like a key and a lock. The key is a protein sticking out from the virus's surface called GP120. And that key is perfectly shaped to fit into the lock on our immune cells, which is that CD4 receptor we just talked about. So when GP120 binds to CD4, the first step of the break-in is complete. But there's a second layer of security. After the key is in the lock, the virus has to engage a co-receptor, something like CCR5 or CCXR4. You can think of this like a deadbolt. It's only when GP120 binds to both the CD4 lock and the CCR5 deadbolt that the door can finally swing open, letting the virus fuse with the cell and dump all its contents inside. And understanding this whole deadbolt mechanism is just incredibly important. Here's why this matters so much. Some people are born with a natural genetic mutation in their CCR5 gene. It basically changes the shape of the deadbolt. The virus's key can't turn it, and that makes them highly resistant to infection. This natural resistance showed scientists that blocking CCR5 is a really powerful strategy for developing HIV treatments. So once the virus is inside, what happens next? Well, let's trace the timeline of an untreated infection. And it's not a quick battle, it's a long, drawn-out war that's fought over many years. In the first few weeks, which we call the acute phase, the virus just replicates like crazy.
The amount of virus in the blood, that's the viral load, spikes dramatically. And as the virus multiplies, the body's immune fighters, those CD4 cells, are destroyed, causing their numbers to take a really sharp initial dip. Okay, so after that initial acute infection, the immune system rallies and fights back. It pushes the virus into a long period called clinical latency, which can last for about 8 to 10 years. During this time, a person might feel perfectly fine, but underneath the surface, the virus is silently and steadily chipping away at their CD4 cells. Eventually, without treatment, the immune system just gets too weak to fight back, and that leads to AIDS. Now, during that initial acute phase, a lot of people do experience symptoms, but they're notoriously nonspecific. It often feels just like a bad case of the flu or mono, fever, fatigue, aches. And because these symptoms go away on their own as the immune system fights back, the initial infection is very, very often missed. So when does an HIV infection officially become AIDS? Well, the clinical definition really comes down to a single critical number. When a person's CD4 cell count drops below 200 cells per cubic millimeter of blood, their immune system is considered severely compromised, and that's when they're diagnosed with acquired immunodeficiency syndrome, or AIDS. There's also a second way AIDS can be diagnosed, and that's by the presence of something called an AIDS-defining illness. These are specific, opportunistic infections or cancers that a healthy immune system would normally just brush off without a problem. When these start to appear, it's a huge red flag that the immune system has been critically weakened by HIV. Okay, so given how stealthy this virus can be, especially in those early stages, how in the world do we find it? This brings us to our final section, the counterintelligence. Let's look at the modern methods we use for testing and diagnosis. Modern testing isn't just one test. It's a multi-step algorithm designed to be as accurate as possible. It starts with what's called a fourth-generation test, and this thing looks for two things at once: the antibodies our body makes to fight the virus, and a piece of the virus itself, that P24 capsid protein. If that test comes back positive, a second test is done to confirm the result and figure out if it's HIV-1 or HIV-2. The whole process is incredibly effective at catching infections. And this is why that fourth-generation test is such a game changer. It helps to close what's called the serological window. That's the critical period of a few weeks right after infection when our bodies haven't made enough antibodies yet to be spotted by older tests. By also looking for the P24 antigen, which is a part of the virus itself, we can find the infection much, much earlier, and that is absolutely critical for treatment and prevention. So we've taken HIV apart, from its genetic code to its method of attack to the long war it wages in the body. We understand its structure, we understand its strategy, and all of this brings us to a final, really big question. Now that we can deconstruct this virus so completely, what's the next frontier in the battle to finally defeat it? Well, the answers lie in that ongoing pursuit of better treatments, a preventative vaccine, and hopefully, one day, a cure.